Hi and welcome to this video where we look at another important concept for your exam preparation. So we will look at melting and boiling point comparison. So this is a question that comes up in pretty much every paper, but it can be present in so many different forms. But if you know a little bit the general structure or the general logic thinking that you need to have to answer this question, then you will be fine and you will get all the marks. So we're talking about melting and boiling point comparison, and we are normally asked to compare different type of molecules or compounds or structures. So the first thing to identify is which type of bond are we comparing? Is that ionic? Is that covalent or metallic bond? Once you know that, you can think about it as a giant or a molecular structure. And then you need to compare the strength of either the bond. Of course, the strength of the bond is only if this bond has to be broken in order to change physical state. So the giant structures, yeah, it would be breaking the bond. While if you're comparing molecular structures, we're looking at the strength of intermolecular forces. Okay, so if you're comparing the giant, you're likely to be comparing ionic or maybe some of the giant covalent examples that you need to know, or maybe the metallic one. Okay, if you compare just one of the structures, then you need to think about the factors that affect each bond strength. And this relates to the concept of a charge density that I mentioned in a video earlier. And because this is what affects some of the strength of the bonds. So let's think that we're comparing just the strength of bonds, so covalent, metallic, and ionic. There are the two main things that affect the strength of the bond is effective nuclear charge or nuclear attraction, because that as a definition is the actual amount of positive charge that is experienced by electrons. So always think about, okay, how are these atoms held together? Well, in the covalent bond, we have the pair of electrons attracted to the nucleus. Okay, so well, the nuclear structure is attraction is what is going to affect the strength of the bond. Yeah, of course, this decreases with an increase in shielding, so in the atomic radius. If we're talking about ionic bond, then we can compare the charge density because the higher the charge density, the higher the bond, the stronger the bond. But how does this apply to the boiling point? Well, always more energy is required to break it. Okay, so think about what is that bond? Okay, how is that formed, and therefore the factors that could affect the strength of the bond. Always trying to visualize the atoms as like in terms of charge density and the size, because these give us a clear idea about the nuclear charge and or the charge density. Well, if you're comparing molecules, so if you identify that you are looking at covalent bond, just molecular structures, you need to compare the strength of the intermolecular forces, remembering how they arise, but let's not go into detail for that. There are other videos for that. Think about the strength, okay? If you want to have a logic way to get there, think about the difference in electronegativity, because you know that at the end, this is what arises dipole-dipole and hydrogen bond, which are the strongest ones. So the biggest the difference, the biggest is dipoles, therefore the stronger the intermolecular force. Or if you're just comparing molecules that don't have polarity, you're looking at London dispersion forces. And you know that this depends on the number of electrons. So the bigger the molecule, the stronger the force. And how does that apply to boiling point? Well, the stronger the force, the more energy is required to break it. And this is also the nice way to explain it in terms of how do you link, boiling point and strength of the bond. So I want to show you now like three different questions that come up, and they're really different, but at the end is the same topic. For example, this one, explain in terms of crystal structure and bonding why silicon oxide has a higher melting point than phosphorus oxide. So I want you to think about what I said at the beginning, how to get to the answer. The first thing was think about the type of bond. Second, the structure. And third, what are you comparing? What are you breaking? Bond or intermolecular force? Maybe you want to press pause and play again once you're ready to answer. Otherwise, keep listening and I'll show you the marking scheme. First, a few notes that I would take, and that's I think the correct logic thinking to have. So silicon oxide, phosphorus oxide. Okay, so phosphorus oxide, yeah, this is a small molecule. Silicon oxide is a giant structure, and you know that because you should know the oxides in of group, the oxide in a group in period 3. So phosphorus oxide is called pentoxide actually because this is the formula, and then silicon dioxide, we know that this is a giant and this is a molecular, and they're both covalent. We know that because, well, always eye on the periodic table gives you that visual aid. So molecular and giant, so what are we comparing? Well, for giant, we would have to break the covalent bond, but we can say, well, this is a very strong covalent bond. So a lot of energy will be required to break it, while molecular, it's still a molecule, which means that it's, the intermolecular forces would have to be broken. So less energy is required to do that. Keep it like with that thinking, then you can articulate a nice answer. Look at the 4 marks here. Type of structure: giant, molecular or macromolecular, or giant covalent. Strong covalent bonds or covalent bonds needs lots of energy to overcome. 3rd mark. Molecular is simple covalent molecule. And then van der Waals forces, because there's no big difference of polarity. So weak like forces, as says here, between the molecules, or van der Waals forces between the molecule, easy to break, not a lot of energy is required to break. Okay, so this is one example when you're comparing actually 2 completely different structures, but you still needed to explain the bond, the structure, and related to energy. Another one for OCR, as they have the many multiple choices. This is an interesting one. Read it, pause, and give me an answer. Otherwise, follow with me. So trending boiling point down halogen groups. Well, halogens, we know that they are what type of bond? Well, they exist as the atomic molecule, first of all. So they're covalent bond between them, but they're small molecules, so we don't think about the strength of the bond, but the strength of intermolecular forces. They're not in order, of course, but let's think about the trend. If you look at the periodic table, actually, let me draw this in order just to be peaky. So we have fluorine, then we have, so fluorine, chlorine, bromine, and iodine, if we put them in order as the periodic table is. And you know that the size of this molecule increases as you go down the group, which means that London forces become stronger. So covalent bond becomes stronger, where that's actually not even true, because as you go down the group, iodine has a weaker nuclear attraction, so it's a weaker covalent bond. But that doesn't matter, don't even break that, because in fact the boiling point is higher as you go down the group. And this is because of the London forces, because it's a bigger molecule. Not permanent, because they are non-polar. So this is the correct one. And the last one is the big 6 marks, so I will leave you to read it and to attempt it, and then I'll show you the marking scheme in the next slide. But notice that it's similar. It's about the difference in boiling point. If it refers to Pauling electronegativity values, that's a hint about intermolecular forces, because that's how they rise. Okay, so can you guess the key points that we have to comment? Well, with the 3 steps, covalent, because they're all non-metals, so it's a covalent bond, but they're small molecules, so we compare the intermolecular forces. And here I would always suggest you to think about what intermolecular forces are present in each of this molecule, and then how does that relate to the energy required. And here is the marking scheme. Okay, so same London forces, that's a key one, because they have the same number of electrons. If the set number of electrons, that's a reason. Electronegativity, big is the difference. Then think about the intermolecular forces in each, and then about the energy. Notice how a 6 mark can be so easily distributed in terms of marks. So I hope this revision helps to think about the key things to know about, to mention about the comparison of melting and boiling point. Okay, and if you have this logic, systematic thinking, you are able to get all the marks, no matter if you have a short answer, a multiple choice, or an open question, like as big as 6 marks. Okay, I hope this is helpful, and I hope to see you in the next video tomorrow.